we were talking about this architecture, guys, in which we had the vanilla RNN unrolled in time and being represented like a deep neural network in which all layers have the same weights. So guys, remember the formulation. It was just simply the formulation, guys. So if you think about it, this whole notation is all about this formulation. So it's simple, and it's all about this formulation. So in this formulation is so simple, and this will be your first homework. You just maybe for most of you, you're taking my third course, so this will be the homework, guys. Very happy. It's a very easy homework in which you are going to implement the vanilla's forward function, which is only this. So it is very simple, and you can do it in 2 minutes in MATLAB or Python, whatever platform of your choice. I don't want you to use any libraries, just multiplications, but it is not indicated here. I'm going to indicate it in the homework description when I upload it to World Online. I'm going to be asking you something funny. So this will be RNN's forward function. You won't have the backward function, so you won't have the chance to back propagate any error or loss function, right? Okay, you won't. But I'm going to be asking you to find weights for a specific problem. And the problem I have in mind is saying at the output, so in your using this implemented RNN, I'm going to ask you to implement a simple network in which you detect or classify the length of the sequence as odd or even. I repeat, so let's try to understand this problem. I'm going to write it in the homework description, but so it's going to be a sequence of length n equals 1. So n will be equal to, let me get the annotation. So n will be equal to 1. So this will be a single vector, like a scalar, okay? So each time you are feeding a single value, for example, 1, 3, 5, the values are not important. What I'm saying is, given the values, the output will always be the length of the sequence. So when you first output, it's going to be, for example, 0, indicating odd. The second one will be 1, 0, 1, 0, 1. You will have to find the necessary weights that could do this job by thinking about them, not back propagation. So what I'm asking you is just prepare this RNN forward function in your code, then decide on your hidden weight numbers. This k could be anything from 1 to k. Choose it, you choose it. And assign weights manually. Think about it, get a pen and a paper, some scratch paper, and work on numbers which will do this job for us, guys. So which will automatically give us these values. So without back propagation, you're going to try some weights, and you'll have to think about, well, it's switching from one to another, so I'll have to do some mathematical trick which will switch on and on, maybe multiplying with -1 each time. That's a good idea. Kind of, you're going to do something. Define the activation function and implement this odd-even sequence. That will be your homework. The reason I'm giving stupid homework like this is, I want you to understand the idea of states changing with the sequence, and I want you to find those states that work like this. So it's a stupid assignment, but I think it's nice. So it's for the end of this month, and you're going to upload it to level 1. Okay, anybody questions about the homework? Everybody's crystal clear today. Wonderful. Okay, so we have our first homework. Very nice. So guys, the structure I have defined in the previous hour was a type of vanilla RNN, which we call to be a many-to-many model, because the input was a sequence of S, which is many, more than one, and the output being a sequence of, again, S, which is many, more than one. That's not necessarily the case for all applications of RNNs. You could get an S-length sequence as input and S-length sequence as output and call this a many model. However, by very simple changes, you can create different types of vanilla RNNs. And actually, the types of vanilla RNNs you can create will correspond to different type of sequence problems we have seen in the previous week. Remember the last slides of the previous week, we have talked about different problems. One input given, many inputs being taken. Many inputs given, or one input being taken. So with many simple changes in this model, mathematical changes, not even mathematical architectural changes, mathematics won't change those formulas, we are going to define different types of vanilla RNNs, okay? And thus, we can apply those different types of vanilla RNNs to different types of sequence problems. Good. We're going to discuss one-to-one, one-to-many, one-to-one with delay, many-to-one, and many-to-many with delay definitions. And if you've seen Coursera, Andrew Wenge's course, he goes through all these examples as well. And I think that's an important step to understand sequence problems and how they are treated using RNNs. If you want to understand this, you have to go over this different types of vanilla RNNs and their applications with multiple input and output relations. Okay, so we start with one-to-one RNN. Let's change our model to one-to-one RNN. I repeat, I'm not saying one-to-one RNN with a delay. There is no delay. In this RNN, you give one input and you get one output. So it is like calling the vanilla RNN only once for a fixed sized output. So in this case, a one-to-one RNN is no different than an FFN because you're not using the next state that you come across here. Because if you call it with one input and get a one output, sorry, let me get it, that's my pen. Okay, so at the output, there will be A1, T2 to AK, T2, right? But I'm not using it. I'm not using it because I get the input, I got the output. So it is no different than an FFN. So if you don't want to correlate your RNN with your previous calls, you don't need a memory. So if you feed 0, 0, 0, 0, 0, 0 each time you call it, and you get immediately the output, this will be a one-to-one RNN, and it will be no different than an FNN. So this is the trivial case. So this is not a type of an RNN, but we're trying to investigate what happens when we apply different strategies when we are applying input and accepting output. Because if you're going to do this, just use an FNN. It's meaningless. Okay, I think you got it. It was a trivial case. Let's get to the other one. Okay, one-to-one RNN. So a nice example is a random sample generator with a specific distribution. So you just give an input and get out. That's a good one. So, when I said if you're not going to use this input, just put zeros always, it will be no different than an FNN. However, if you're going to define a one-to-one RNN, which would make sense as a recurrent neural network, it would be like you call this function and you get an output. Then, when you call that function again, you'll be using the next state. With another input, you'll get another output. A nice example of this kind of example is a random sample generator with a specific distribution. For example, you are trying to simulate getting a card from a deck. Because the first time you are getting a card from a deck, the probability of getting a card from that deck is the same. So the distribution does not change. But if you get that card, put it on the table, and try to get a second card in which the first card is not included. Actually, you are choosing that card from another distribution. In that case, you have changed the distribution. So it needs a memory. That case, you'll be using the next output. And that would be a proper one-to-one RNN example, not an example that you could use an FNN with. That would be a proper RNN example. So one-to-one examples exist in RNNs. Okay, so I think the difference between an RNN being used for one-to-one example and which is meaningful. I'm getting cards from a deck example. Okay, I continue. One-to-many example, good. One-to-many example is you have one input and you are getting many outputs. So this is like calling your vanilla RNN for multiple times using the same input. Because if you want to call this RNN over and over again, you'll need an input. And if you have only one input, it will be the same input you're always just filling in. So in this case, if we want to make this work as a one-to-many RNN, we simply feed the same inputs and we observe the sequence of outputs from 0 to S or 1 to S, whatever the start time you're talking about. So the output sequence can be varying or fixed length. Depending on the times you're feeding the same input, S times or whatever the S value is, some other value, always the same input, you'll get a sequence of outputs. So this is a one-to-many RNN. So if you have a one-to-many RNN problem, like, I don't know, any ideas? If you have any ideas, think about it, I'm going to ask. So this looks like a fixed length output for S, but how to make it variable length? Just like I said, you could keep calling this with the same input and the output sequence length may change. Okay, good. Or you could stop when you see a certain input. So you could implement something like continue getting outputs, feeding the input until you see a special sign, like a dot, end of a sentence. Maybe this network was a network in which you feed a single word, maybe, an idea. And getting that single word, it constructs a sentence to you of some length you don't know. So that's a nice idea, right? You feed an input, you get an output. What other examples comes to your mind? If anybody has some idea, you could share with us. What kind of an example? There's if you've printed the slides, there's an example in the next slide, but other than that, if you have any ideas, I'd like to hear. Maybe related to your projects. No? Okay. Okay. So another nice idea is, this has been done. You feed the scale of the song. You say A harmonic minor, and it provides you a, piano piece of some length you don't know in A harmonic minor. So that would be a nice thing to do. Anybody could try if you're into music and if you want to try this in your projects, well, that would be a nice project. They are already being done. But it will be okay to try it in a graduate course project. So don't worry, you don't have to just write a paper about it, but that would be a nice example. Okay. Now I'm going to change the first example, one-to-one example, to one-to-one with delay. Because in some cases, the output, because of the definition of the problem, may need a delay. And that delay could be specific, like 3, or a delay that you don't know. You will be getting the output until you see that output. Let me just elaborate. So this is like calling the vanilla RNN for multiple times using the same fixed sized input vector because it's one-to-one. Because of this one, I'm always giving the same input until I get the output after some delay. Okay, that delay can be defined fixed delay or a varying delay depending on your problem. So how to define it in our problem, guys? So it's always the same architecture as one-to-many, but we only consider the last output. The intermediate outputs before the last output are simply ignored. If you ignore them, that makes it a one-to-one RNN. Well, here something strange comes to mind. I mean, okay, one-to-many was, let's remember one-to-many was the same example in which we have fed inputs and we got outputs. And one-to-one with delay is again, we feed inputs and we get outputs. So what is the difference between them? The difference will be important when we are training them, because ignoring these outputs means you will not create any loss related to these outputs. So when you're training them, there will be no derivatives back propagated from the loss that is created with these outputs. The only loss will be created by this guy. But for the previous one, which is one-to-many RNN, in which every sequence of the output counts, on that case, we will calculate the loss for each output, and we will create a derivative from each loss, which will be fed to the computational graph. So their difference architecturally cannot be seen in the forward operation, but when we are trying to train them next week, that difference will count, guys. Okay. Okay, so so what is it with delay? Why wait? Maybe repeat. Is it fixed or varying length? This depends on the problem, and this will depend on the problem, and we are going to discuss that in future in many examples. And about the thing I just said, how do I know that this is a one-to-one or one-to-many model? Because the forward operation doesn't show any difference to us. We just simply ignore the output. Who is ignoring the output? Well, just like I said, the loss function is ignoring the output. So in the forward operation, that ignore doesn't make sense, but in the backward operation, it makes pretty much sense, guys. It's just the idea. Okay, good. Okay, example. Why do we need a delay? Any ideas that you want to share? Evet arkadaşlar, dersi Cuma günü yapmanın etkileri herhalde. Yani Cuma günü insanlara akşam 8'de one-to-one RNN'lerde delay'e bir fikir verir misiniz deyince hiç kimse cevap vermiyormuş. Yani pazartesi farklı olabilirdi. Okay, I'll get back to English. So in the next slide, if you have already printed them or if you could see them on your computer, you'll see that answer. The best example is a control system. You know, some of you know that we are already working on this with Oğuzhan Hoca. Because systems usually create delay. If you're trying to simulate a dynamic system, given an input, trying to get the output, you have to simulate the delay as well. And if you know the natural delay of that dynamic system, and if you know the sampling rate that you feed the input to the system, that you could apply that fixed length delay for your system to learn that dynamic system behavior so that your RNN can simulate dynamic systems. Actually, simulating dynamic systems using RNNs is an old topic. In the 80s, when these RNNs were first introduced, the first thing people tried was this, because they were mainly mathematicians, and when they see a feedback connection, that's a control system, well, we could just imitate the control system behavior with this. That was the first thing they tried. I mean, it didn't work well because of the reasons we are going to discuss next week, because it's very difficult to train recurrent neural networks, especially if the sequence length is long. And they were not very successful, but today we have much more successful examples of those. And we are going to discuss about them as well. Okay, so they can only, a dynamic, if you want to emulate a dynamic system, you can model it as one-to-many with delay if you have a single input, or if you have a varying input, which is the case for most dynamic systems, many-to-many with most probably a delay, which we are going to cover in the following examples. Good. Many-to-one. And this one also looks like the one-to-one with delay example, because in one-to-one with delay, we were feeding an input and waiting for a single output, right? And we were ignoring the rest of the output. Ignoring meant that the loss function was taken for only the last output. But different from one-to-one with delay, many-to-one RNN is simply an RNN with an input sequence which is changing through time. So the input sequence is changing, and at some point you get a value. So it's like one-to-one with delay with varying inputs. Okay, so you're ignoring this output. Ignoring meant that you already know. We don't calculate a loss for that. Okay. So training wheel then will be the same. However, the input will be different. We simply use a different input. Example. Just somebody just. Okay, somebody is giving an example, or somebody is trying to make their children stop talking. Which one?
We might give it a sentence, and it might tell us which language is it.
Wonderful,
maybe.
Wonderful example. Thank you, Sanem. Is it Sanem? Yes, thank you, Sanem. Yeah, exactly. Words, 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 words. And you will need many words because in most languages, some words are pronounced similar. For example, I start my word using the word normal. If I don't see the second sentence, I could think that this is Turkish, German, or English, or I don't know, whatever language uses normal or pronounces the word normal. Same. Exactly. And the example I provided in my slides was this, this one. Is this bird flying or just it is hanging in the air? Somebody is a Jedi just holding a dead bird, filled dead bird up the sky. Which one? Well, many to one example could answer you that. Flying or Jedi holding the filled bird. Anyone between is can be only told by a many to one example. Okay, simple. We're following. Many to many with delay. That's nice. That's one of the most important architectures. In this many to many delay, there's something you should be careful about. This is like many to one architecture, but you just don't ignore all the inputs but the last. Because remember the one to many, many to one, you have ignored every output but this one. You don't do that. You ignore some of the first, which is spent along the delay, but the rest of the output after the delay is counted, which means you are calculating loss for them, and you're feeding the loss to your model back. Okay, I think this was simple as well. Any examples different than the example in the next slide? Because next slide is a language example. No examples? Okay, I'm trying to make you think about examples which will give you a project idea. The simplest example is language translation, guys. As I told you, this is the real deal. And actually all natural language processing shifted to RNN domain because of this. We could construct many-to-many models with delay. Because in order to translate a sentence, we need a delay. Think about the translator. They always follow the translation a couple seconds later because they need to understand what kind of sentence is coming in. And in order to understand a sentence, you need time because the languages that you are translating in between are most probably structured in a very different manner. A sentence being constructed in Turkish in one way is constructed in just in a reverse manner in English, for example. That's why you need a delay. And that type of delay could be different for all applications. For language translation, that varies. When you're translating a sentence, one sentence from English to Turkish, the delay will be different. For another sentence, the delay could be much more or less. We don't know. So for different examples, this is the problem. And most of the time, we are going to be dealing with problems which are called many-to-many with delay. Okay then. I think that concludes what I'm going to discuss today. There are a couple of suggested readings, guys. I'm going to provide these. And they provide many things about these examples. And actually, there's even an example about recurrent neural network model in Python, which is the homework to you. If you want to shift to Python, just use them. And there are very nice examples, just follow them. And I think that's it. I think we're about 1.5 hours. If you don't have any questions.